Good evening, Lamai. Let's start the session for today. Today we are supposed to discuss about the hydrogen emission spectrum, right? That is the lesson today, right? When we are discussing about the story of the atom, right? We had mentioned about the hydrogen emission spectrum. Where? So this is one of the failures of the Rutherford's atom, right? Rutherford's nuclear model. There were two failures. Right, one was the atom was unstable, not stable, according to Rutherford's model. And the second thing was the Rutherford's model was unable to explain the origins of the hydrogen emission spectrum. Right, today we are going to discuss about the spectrum and the solutions given by the Niels Bohr to describe the origins of the hydrogen emission spectrum. Right, so that is going to be the discussion today. Right. First of all, before going towards the spectrum, before going towards this atomic spectrum, the hydrogen emission spectrum, right? The atomic spectrum, the emission spectrum came from the hydrogen atom. First, let's discuss a bit about the concept of spectrum or concept of spectra. Right? What is meant by a spectrum or a spectra? Last day we had discussed about that thing, right? So, what I have told you, a definition or the meaning of a spectrum or a spectra, it might be spectrum. Right? It is like this. It is a spectrum is an arrangement of radiation, arrangement of electromagnetic radiation in increasing or decreasing order of frequency, wavelength, or the energy of the electromagnetic radiation. Right, a spectrum consists of radiation which are arranged in increasing or decreasing order of wavelength, energy, or the frequency. Right, if you need to get some idea, right? Let's say you have a source which is radiating, which is emitting electromagnetic radiation. Say this guy is coming up with, let's say, it's an atom or something, radioactive source, radiating source, right? Coming up with 250 nanometer radiation. Let's say some 150 nanometer radiation, some 600 nanometer, some 400 nanometer radiation, as well as some 300 nanometer radiation. Right? So if you arrange this radiation coming from a radioactive source or as atom even in the in increasing or decreasing order of wavelength, frequency, or the energy, we can call it as a spectrum. See, it's like this. So if you arrange these things in increasing order of wavelength, let's say wavelength increasing order, right? Wavelength increasing towards this direction, right? So if you arrange this like this, so you are starting with 150, let's say the 150 nanometer radiation or the electromagnetic radiation, right? So then you have the 250 coming up here. Then you have the 300. Let's say here is 250, is 300. Then you have the 400 and 600. 400, right? Okay, so let's say 400 here, some 600. So this is a kind of arrangement of these few radiation, these few electromagnetic waves in increasing order of wavelength. So this is called as a spectrum. Spectrum, right? Arrangement of radiation, electromagnetic waves, right, in increasing or decreasing order of wavelength, energy, so right, frequencies can be referred to as a spectrum. So there are two kinds of spectrum. There are two kinds of spectra, right? One is this kind. This is referred to as a line spectrum. This is referred to as line spectrum. That means in a considerable range. In a considerable range. So the range of this spectrum is 150 to 600. in a constrained range, only few electromagnetic waves are appearing. Only few electromagnetic waves are appearing. So these are line spectra, right? These are considered as line spectra. In the constrained range 150-600, you can see few waves are appearing, not all the waves. I mean, 150 is there, but 151, 152, 153, those radiation are not there. Those waves are not there. After the 150, you will come up with the 250 lambda and the 300 lambda nanometers, like that. You don't have the 151, 150, 150 like that. It's not a continuous spectrum. It's referred to as a discrete spectrum, the line spectrum or a discrete spectrum. Some spaces in between are there. Right? Not all the radiation in the constrained range are available. Only few are available. Those are referred to as line spectrum or line spectra. Right? So basically atomic spectra, the spectrum or spectra coming from atoms are referred to as line spectra. Right? Such kind of a line spectra has been observed by an excited hydrogen sample as well, which is known as the hydrogen spectrum. Right? So that is what we are going to discuss today. And this was unable to explain by the Rutherford's nuclear model. Right? That was one failure of that model as well. Right? Okay. So let's come up with the hydrogen emission spectrum, the theory behind that thing. So you see the spectrum here appearing. Right? This is the spectrum. So the line spectrum they had observed with the sample of excited hydrogen atoms. Right? So they came up with a sample of excited hydrogen atoms. Right? So sample of excited hydrogen atoms, right? That means sample of excited hydrogen atoms, right? From a sample of excited hydrogen atoms, right? Sample of excited H atoms. They have observed this thing. So excited hydrogen atoms from that sample, right? From this emitted radiation, if they are to arrange, right? This is an excited hydrogen sample, and that will emit radiation like this, right? If you are to arrange this emitted radiation, these emitted waves in increasing order of energy or the frequency, you had observed this thing, right? From an excited hydrogen atom sample, right? So that is why this is referred to as the hydrogen emission spectra. Hydrogen emission spectra from the emitted radiation from excited hydrogen atom samples, right? They have observed this kind of a specific pattern, lines with some specific patterns, right? As the hydrogen emission spectra, right? So today we are going to discuss about that thing. So this is the pattern they have observed as the hydrogen emission spectrum, right? See, so going towards the higher energy region, this is the higher energy region, right? They have seen this kind of some specific pattern of lines are appearing. Let's try to explain this stuff and the origins of this thing, right? Okay, right. So first of all, let's discuss about the patterns they have observed, the scientists have observed, right, with this hydrogen emission spectrum. After that, we can think of the solutions, the explanation for origins of those lines, those patterns, right? So actually, this thing has been observed even in 1860s, in mid 1800s, right? They have observed this pattern, right? Even though they have unable to explain the stuff, the origins of the patterns, right? So what are the basic patterns they have observed? First of all, let's grab that thing. Let's discuss about that thing. What are the basic patterns they have observed with this hydrogen spectrum? First, come with those. Then we'll can think of explanations for those appearance of those patterns, right? So the major three things have been observed as patterns. Major three things have been observed as patterns, right? What are those? See, the first thing they have observed as patterns, right? So they have seen some series of lines. That means so some bunch of lines, right? Bunch of lines coming, right, as a series of lines. So this bunch, this and this and this, right? So these are referred to as series of lines, right? The first series which is appearing, right, at the higher energy region is actually observed by a scientist called Lyman. This series of lines is observed by the scientist called Lyman, so that it is named as the Lyman series of lines. Lyman series of lines. Lyman series. Right? And then another bunch of lines coming as a series is observed by Balmer at the lower frequencies, at the lower energies than the Lyman, and that is referred to as the Balmer series. Balmer series. Right? Then like that, some other series which is close to the Balmer but at a lower energy range, lower frequency range, has been observed by a scientist called Parshan, and it is referred to as Parshan series. And two scientists called Brackett and Fund observed some lines appearing, actually lines overlapping with each other. So that two series of lines are referred to as Brackett and Fund, which overlap. Right? The series are overlap. Right? So those are the series of lines observed in hydrogen emission spectrum. Right? So let's discuss about the patterns of these things. Patterns. So when it comes to series of lines, some common pattern can be observed with all the Lyman, Balmer, and Parshan series of lines. What is the common pattern? The common pattern is going towards the higher energy region, or one can say going towards the higher frequency region. The energy and the frequency both are same, right? Energy and the frequency both are same, right? is equal to h mu, no? Is a constant, no? That means energy increasing direction means same as the frequency increasing direction, right? So when going towards the higher energy region or higher frequency region, they have seen the lines in a constituent series, comes closer to each other, or one can say the gaps between the lines of a constituent series decrease. The gaps between the lines of a constituent series decrease, going towards higher energy region, higher frequency region. That is what they have observed. Even this Balmer series, you can see the gaps between the lines going towards a higher energy region, higher frequency region. The gaps between the lines of a constituent series has decreased. Even in the Parshan, you can see gaps between lines has decreased, going towards higher energy, higher frequency region. That has been observed with both with the Lyman, Balmer, and Parshan, all of those series, right? So that is one specific observation, special observation they have seen, right? Gaps between lines decreased, right? And when it comes to gaps between lines, another specific thing has been observed, right? That is what? That is like this. So if you think of the Lyman series and take the second line onwards of the Lyman, if you take the second line onwards of the Lyman, what is the second line? It is like this line. For any constituent series, the first line is the line with the lowest energy of that series. So that if you are considering these series of lines, which is considered as a Lyman series, the first line is this one. The line with the lowest energy. This is the second line, this is the third line, fourth, fifth, like that, right? So when considering series of lines, right, going from first line to the ultimate line, the gaps between the lines decrease. That is what we have, right, discussed as the first point, right, first observation. And the second observation, very important observation about the gaps of these lines, right, is that actually if you take the second line onwards, from the Lyman series and copy that thing and paste, at a lower energy region, you will observe that as the Balmer series. If you copy the second line onwards from the Lyman, second, third, fourth, fifth, sixth, like that, if you are to copy the second line onwards from the Lyman and paste it, right, at a lower energy region, right, those will be the gaps between the lines of the Balmer series as well, right? If you copy this thing and paste it here, those are the lines, those will be the gaps of the Balmer series as well. If you are to copy the third line onwards of the Lyman, if you copy third line onwards of Lyman and paste that thing at an energy region which is with lower energy than the Balmer, you will see the partition appearing. If you copy the third line onwards from the Lyman and paste it here, that is actually the partition series. Right? That pattern is also observed. Right? So that means basically the gap between the second and third line of the Lyman, the gap between the second and third lines of the Lyman is actually same as the gap between the first and second line of the Balmer. That is what it means. Right? The gap between the second and third line, gap between the third and fourth line, the gap between the third and fourth line of the Lyman is going to be same as the gap between second and third line of the Balmer. That is what it means, right? If you copy the second line onwards from the Lyman and paste it here, that will give you the same gaps as the gaps appearing at the Balmer series between the lines, right? The idea is clear, right? So if you think of like the same thing, right? If you think of the third and fourth lines of the Lyman, that gap between the third and fourth lines of the Lyman, that will be equal to the first and second line of the partition, the gap between that, right? The idea is clear. So we have discussed two patterns now. What is the first thing? That is when going towards high energy region, the gaps between separate lines decrease or gaps becomes closer to each other when going towards high energy region of considering series of lines, right? That can be observed with Lyman, Balmer, and partition, or the series of lines, right? And the second thing we have discussed is, right, if you copy the second line onwards and paste it at a place where at lower energies, right, you will observe the Balmer series. And if you take the third line onwards and copy that thing, copy the third line onwards and paste it there, you will observe the partition series, right? That trends are appearing with this series. And what else they have observed? Right? What else they have observed? The third thing, the third important stuff they have observed. Earlier we had discussed about the gaps between spectral lines of a constituent series. Now we are leading to gaps between spectral series. That means these gaps. Gaps between spectral series means these gaps. Gaps between the Lyman and Balmer. Gaps between the Balmer and partition. Gap between the partition and bracket. So they have observed another pattern there. Even though gaps between spectral lines of a constituent series decreases going towards high energy region, gaps separating the series of lines, gaps separating the series will increase going towards high energy region. Gaps separating the series will increase going towards higher energy region or higher frequency region. That is another major point to grab from this pattern, which is referred to as the hydrogen emission spectrum, right? Gaps between spectral lines decrease going towards higher energy region, but gaps separating spectral series will increase going towards higher energy or higher frequency region. That is clear? Okay. Right. Few more stuff. For few more important stuff they have observed. This is about that. So they have observed the first four lines of the Balmer series. The first four lines of the Balmer series are colored. Those are the first four lines observed at the hydrogen emission spectrum, right? So the first four lines of the Balmer series are colored. There is also another specific observation they have seen. the scientists have seen. The first 4 lines of Balmer are with colors. The first line of the Balmer is with red color. The second line of the Balmer is with green color. Third line of the Balmer is with blue color, and the fourth line is with purple color. Right? So the first line, the red color line, is known as H alpha. Is referred to as the H alpha, the first line of the Balmer. And the second line is known as the H beta. They have named those lines, the colorful lines of the hydrogen spectrum. H gamma, and the fourth line is referred to as the H delta. So we have 4 colorful lines in our hydrogen emission spectrum. Those are the first 4 lines of the Balmer series, which the Balmer has observed. Right? The first line is red colored. Next line is green colored. The first line is named as H alpha. The colorful lines are named, right? The second line is named as H beta. The third line is blue colored, H gamma, and fourth line is actually violet in color, which is known as the H delta line, the hydrogen's delta line, the fourth line, right? Those are colored. So with Balmer series, they have observed some colorful lines as well. These are the observations they have seen with as the hydrogen emission spectrum, right? Okay, right. So after the violet colored line, some other few lines also was appeared in the Balmer series, right? So that the scientists said that the first 4 lines of Balmer belongs to the visible region. That is why those are colored lines, and the next lines of the Balmer coming under the ultraviolet region, right? So the first 4 lines, those are colorful lines. Those are coming under the visible region, visible lines, right? Visible lines. And the rest of the lines after the violet, those lines appear at the ultraviolet region. So we can say Balmer series appear partially visible when it comes to those lines in the electromagnetic spectrum, right? So Balmer is partially visible. The first 4 lines of the Balmer coming under the visible region, that is why those are colored. After the violet color, the other lines of the Balmer appears at the ultraviolet region of the electromagnetic spectrum, right? Okay, so that the line 1 should appear at the ultraviolet region, right? After the ultraviolet region. So line 1 series of lines, those lines belongs to ultraviolet region of the electromagnetic spectrum, right? Ultraviolet UV region, and the lines appearing at lower energies than the red colored line, Balmer's first line, appears at IR region, infrared region. Infrared region of the electromagnetic spectrum. Right now, that is how these lines belongs. That is the regions these lines belongs in electromagnetic spectrum. Right? You know about the electromagnetic spectrum. There are a few regions in the electromagnetic spectrum. Right? So the 2 regions near to the visible is actually ultraviolet and the IR, right? So those are 2 regions here appearing with the spectral series, right? Okay, those are things they have observed. These are special things they have observed. Again, I am telling you the special points there. The first thing, it is about the gaps between lines of a considering series of lines in a considering series, right? So gaps between lines will decrease going towards higher energy region of a considering series. That's first thing. Second thing, gaps between spectral series will increase going towards high energy region. And then you have seen that the gaps between the first two lines of the Lyman is equal to, sorry, second and third line of the Lyman is equal to first two lines of the bar, right? Gaps between the second and third line of the bar is equal to third and fourth line of the Lyman, like that. Or gap between the first and second of the partial is equal to third and fourth of the Lyman, like that. Second and third of the bar, like that. So that copy paste stuff can be done. So if you are to take the second line onwards of the Lyman and copy that at a lower region, that will give you the gaps between the lines of the Balmer series, like that. Idea is clear? Those are the major observations they have seen, and the Balmer series was with some 4 colorful lines. The first 4 lines of the Balmer were with colors red, green, blue, and violet, right? Those are the observations, right? Keep that in mind. Those will be frequently asked in questions, even in the MCQs, right? Okay, that is done. That was the observation with the scientists. Even before 1900, right, they have seen this hydrogen spectrum and those patterns, right? They have identified those patterns. But the problem was, with that age, no one was being able to explain the origins of these spectral lines coming from the excited hydrogen atom sample. And 𝐵𝐴 is the scientist. 𝐵𝐴 was the scientist who came up with a good, acceptable explanation for the origin of these spectral lines of the hydrogen atom spectrum. Let's discuss about that explanation given by the 𝐵𝐴. Right? 𝐵𝐴 said, right, to come up with these kind of spectral lines, to originate these kind of spectral lines with these kind of pattern from excited hydrogen sample, he said the hydrogen atoms in this sample should be with these kind of energy levels in them. The electrons of hydrogen atoms in this excited sample should come up with these energy levels to give off this kind of a pattern as the hydrogen atom spectrum. That is what 𝐵𝐴 said, right? 𝐵𝐴 කිව්වේ ළමයි, 𝐵𝐴 කිව්වේ excited hydrogen atom එකකින් මේ වගේ pattern එකක් hydrogen atom spectrum එක විදිහට මේ වගේ pattern එකක් observe වෙන්න නම් 𝐵𝐴 said the hydrogen atom should have this type of energy levels in it. hydrogen atom එකට මේ වගේ energy levels තියෙන්න ඕනේ කියලා. hydrogen atom එකේ තියෙන electrons මේ වගේ energy levels occupy කරන්න ඕනේ කියලා තමයි 𝐵𝐴 කිව්වේ. එහෙම නැත්නම් මේ වගේ spectral pattern එකක් hydrogen atom එකේ ඉන්න බෑ කියලා තමයි යා කියන්නේ. Right? See what else he had said. එයා මෙහෙමත් කියන. Is it to observe this kind of pattern, these kind of patterns with the hydrogen atom spectrum? Is it the hydrogen atoms should have energy levels where the electrons occupy? That is one thing. And those energy levels should follow this kind of a trend. What kind of a trend? The energy levels should follow some trend where going towards the higher energy region, when the energy is increasing, the energy levels, the gaps between the energy levels should decrease. The energy levels should decrease. If only that trend is followed by the energy levels of the hydrogen atom, where the electrons occupy, you would be able to observe this kind of a hydrogen spectrum with these patterns. This is what 𝐵𝐴 said. 𝐵𝐴 කිව්වේ ළමයි මේ වගේ pattern එකක් observe වෙන්න hydrogen emission spectrum විදිහට hydrogen atom එකේ electrons මේ විදිහට energy levels occupy කරන්න ඕනේ. ඒ energy levels වල pattern එකක් තියෙනවා. මොකද්ද? energy levels වල energy එක වැඩි වෙද්දී නැත්නම් when going towards higher energy region, energy levels එයාගේ energy එක වැඩි වෙන පැත්තට යද්දී ඒ energy levels එන්න ලං වෙන්න ඕනේ. The gaps between the energy levels should decrease. The energy levels should become closer to each other when going towards higher energy region. that pattern should be there with the energy levels as well to observe a spectrum like this. That is what Niels Bohr said. හරි. දැන් බලමු එහෙනම් එයාගේ ඒ energy level diagram එකත් එයා කොහොමද මේ patterns observe වෙන හැටි, patterns originate වෙන හැටි explain කරන්න කියලා. Right? හරි. එයා මෙන්න මෙහෙම දෙයක් කියනවා. This is what Niels Bohr said. He said, when it comes to hydrogen atom, the electrons are in the ground state. No? The hydrogen atom එක ගත්තම hydrogen atom එකේ ළම electrons ඉන්නේ එයාගේ lowest energy level එකේ. Right? එයා මේක ළමයි මේ හරියට අරක තමයි හරි මේ වාගේ අර පුංචි hydrogen atom එක කතාව තමයි right? පොඩි කාලේ කතා කරේ. hydrogen atom එක 288 atom එක ආයක තමයි මේ. මේ වගේ 288 atom එක තමයි. This is the origin of 288 atom. Right? එයාගෙන මේ these are energy levels. Right? And also those are given the name quantum numbers. These energy levels are named as quantum numbers. Quantum numbers too. And those are referred to as 1, 2, 3. First quantum number, second quantum number, third quantum like that. So, hydrogen atom energy levels තියෙනවා. Those are quantum numbers. N equals 1, N equals 2. energy levels තියෙනවා. එහෙම නැත්තම් මේ වගේ pattern එකක් observe වෙන්න බෑ. Hydrogen should be with energy levels like this. And normally in hydrogen atom, the electron resides here. Electron තියෙන්නේ N equals 1 වල. Hydrogen atom electron උතන තමයි තියෙන්නේ. But when it comes to excited hydrogen atom, excited කියන්නේ energized hydrogen atom, then the electron could be here, or with one hydrogen atom, another hydrogen atom electron could be here. තවත් hydrogen atom එකේ electron මෙතන තියෙන්න පුළුවන්. එක hydrogen atoms එක electrons එක තැන් වල තියෙන්න පුළුවන්. When it comes to excited hydrogen atoms, excited means energized hydrogen atoms. Electrons are now with high energy levels. Excited hydrogen atoms සාම්පලයක් ගත්තොත් ඕම high energy levels වල electrons තියෙන්න පුළුවන්. Right? Okay. Excited with the normal hydrogen atom is concerned, the electron is there at the first energy level. Excited hydrogen atoms කියලා කියන්නේ energized hydrogen atoms. Hydrogen atoms with some more energy, so that electrons are with higher energy levels there. Some atom is with great energy, that means electrons are with higher energy. So මොකක්ද කොහොමද කියන්නේ? එයා කොහොමද මේකේ ලයින්ස් ඇති වෙනවා කියලා කියන්නේ? එයා කියන්නේ මෙහෙමයි. එයා කියන්නේ මෙන්න මෙහෙම concept එකක්. The ideal concept is like this. Right? He says these energy levels, when considering these energy levels, those energy levels are with some characteristic energy. ඒ කියන්නේ ළමයි n equals 1 ගත්තට පස්සේ n equals 1 එකට යාට characteristic energy එකක් තියෙනවා. n equals 2 ගත්තම energy level යාට characteristic energy එකක් තියෙනවා. n equals 3 ගත්තට පස්සේ the third quantum number, third energy level, it is with the characteristic energy. So energy level ගත්තම පස්සේ ළමයි යාට characteristic energy එකක් තියෙනවා. හරිද? එතකොට ගත්තොත් මෙහෙම energy level ගත්තොත් යාට මෙච්ච energy එකක් තියෙනවා. මම උදාහරණයක් ගන්නනේ ඔයාලට තීරණ භාෂාවෙන් කියන්නේ. Right? හරි හිතන්න මෙයාගේ මේ first energy level එකේ energy එක 10 joules කිය. හරි. මේකේ energy එක නිකන් හිතන්නකෝ 30 joules කිය. මේකේ energy level එක energy එක නිකන් හිතන්නකෝ right 38 joules කිය. So energy levels are with some characteristic energy. These are referred to as quantum numbers. Those are with characteristic energy. The idea is this: if electron is to occupy this energy level, if electron is to occupy one of these energy levels, that means the electron should have that characteristic energy of the energy level. That is the idea here. That is what Niels Bohr said when he introduced the energy concept to the hydrogen atom. He said hydrogen atom is with energy levels, right? That energy levels are related to the energies of the electrons, right? If electron is to occupy such an energy level, it should have the characteristic energy related to the energy level. That is the idea. So හිතන්නකො n equals 1 වල වගේ electron එකක් ඉන්නවා කියලා. ඒ electron එක n equals 1 වල ඉන්න නම් මේ electron එකට තියෙන්න ඕනේ 10 joules of energy. if some electron to appear at n equals 2, that electron should have the characteristic energy of the n equals 2, 30 joules. If some electron is to occupy at here n equals 3, that electron should have 38 joules according to this diagram. Alright. Alright. This is what it says. Right? Okay? Right. So let's say if an electron comes from here to here, let's say this there is electron appearing at this appearing here at here, which is 30 joules of energy, and it needs to come to the n equals 1. Let's say that electron jumps to n equals 1. Now comes to n equals 1. Earlier it was here with 30 joules energy. When it was here, it was with 30 joules of energy. When it is coming to here, now it is with 10 joules of energy. So what happens to the excess energy? Electron මෙතන are 30 joules තිබ්බා. දැන් යා මෙතනට ආවට පස්සේ දැන් යාට තියෙන්නේ 10 joules. So ඉතුරු energy එක මොකද වෙන්නේ? Energy can't be destroyed. Energy can't be destroyed. So what will happen to the 20 joules of energy? Yes, Lamai, when electron coming to a low energy level like this, when electron decrease its energy, that electron will emit the excess energy it had. That means 20 joules of energy it had as a electromagnetic radiation, as a electromagnetic radiation, as a photon of energy, as a photon of energy. So it will release energy photon, which is it 20 joules of energy. That is what it is doing, right? When electron so the point is if an electron needs to occupy an energy level, electron should have the same energy as the characteristic energy of the energy level. That is the first point, right? So if an electron occupies here, it should have 30 joules of energy, which is the energy of the energy level. If electron needs to come to here, it should have only 10 joules of energy, which is the energy of the energy level. So that if electron needs to come from here to here, it needed to release 20 joules of energy to occupy this level, right? To occupy this level, it should have only 10 joules. No? So excess of the other 20 joules should be released. So that electron will release that thing as a energy photon. Energy photon. So that energy photon will have the excess of energy, which will be released, right? Okay, that is how the electrons of the hexadecider atom comes to a low energy level by releasing electrons, right? The Niels Bohr said, from these releasing electrons, from these energies of the releasing electrons, the spectrum is originated. That is what Niels Bohr said. When electrons are coming from high energy levels to low energy level, when electrons are transiting from high energy to low energy like this, from the released photons, from the released photons of energy, right? These spectral lines are observed. That is what it says. That is what Niels Bohr said. මේ වගේ high energy levels of the electrons hexadecider atom එකක low energy level එකට එද්දී ඒකෙන් emit වෙන photons වලින් නැත්නම් ඒකෙන් waves වලින් wave photons වලින් තමයි hydrogen emission spectrum එක හැදිලා තියෙන්නේ කියලා Niels Bohr කියන්නේ. Right? So when the electrons are jumped towards n equals 1, when electrons are jumped towards n equals 1 from the high energy levels like this, some energy photons are released, right? When electron jumps from high energy levels towards n equals 1, some energy photons are released like this. If you were to arrange those electrons coming towards n equals 1 in the order of increasing energy or frequency or lambda, you will observe the Lyman series. That is what Niels Bohr said. හරි මේ විදිහට ළමයි higher energy levels වලින් electrons n equals 1 වලට transit වෙද්දී n equals 1 වලට එද්දී ඒකෙන් release කරන photons වලින් තමයි Lyman series එක හැදලා තියෙන්නේ කියලා එයා කියනවා. Right? When this is the smallest energy line, smallest energy transition of the Lyman series, that should be this. නේ electron මෙතන ඉඳන් මෙතනට එද්දී නේද? මොකද වෙන්නේ? එයාගේ අර තිබ්බ excess energy එක එයා release කරන photon එකක් විදියට. හරි? සරලව කිව්වොත් that photon, one mole of photons will carry this gap, right? අර නිකන් අර 984 kilojoules per mole H will be released for mole of photons per mole, right? That is the energy gap between these two. මේ වගේ transition small එකක් සිද්ධ වෙද්දී release වෙන energy එක තමයි that is equal to energy gap. හරි මේ කතාව පැහැදිලි ඉන්නේ. Release photon එක energy එක හොයාගන්න පුළුවන් if you take the energy gap between the two corresponding energy levels. Alright, you take the energy gap between the two corresponding energy levels, you can come up with the energy of the photon release, right? Shape ne? The idea තමයි apply with මෙතනින් මෙතන electron release වෙද්දී ඒ photons වල energy එක හොයාගන්න පුළුවන් by considering the energy gap of the two corresponding energy levels, right? හරි. ඉතින් ඔය විදිහට n equals 1 වලට electrons එද්දී transit වෙද්දී release වෙන photons වලින් තමයි Lyman series එක හැදලා තියෙන්නේ කියලා Niels Bohr කියනවා. When electron coming from the nearest energy level to the n equals 1, that means n equals 2 to n equals 1, from those energy photons the first line of Lyman has created. When electrons are to come towards n equals 1 from the next nearest, the n equals 3, from the n equals 3 to n equals 1. From those photons, right, the second line of the Lyman has been created. This is how the Lyman series of lines have been created by the photons released when the electrons are coming towards n equals 1 from high energy levels. That is what Niels Bohr said. Right, නේද? එහෙනම් බලන්න කොහොමද බාම හැදෙන්නේ කියලා. Let's discuss about the Balmer series. When electrons are coming towards n equals 2 from high energy levels, like this, from those released photons, the Balmer series has been originated. Alright. So the electrons are coming towards n equals 2. From those released photons, the Balmer series of lines has been originated. Right now, that is how the Balmer series originated. Alright. When electron is coming from the closest energy level, n equals 3 to the n equals 2, that is the reason for the first line of the Balmer. When the electron is coming from the next higher energy level towards n equals 2, that is the reason for the second line of the Balmer, green line. This is the third line of the Balmer, this is the fourth line of the Balmer. As energy gap increases, the energies of these lines will increase. So energies of these lines will represent the energy gap between the two energy levels of electron transition, right? So energy of the photon is equal to the energy gap. The 2NT is equal to 30 minus 10. The energy of the photon is equal to energy gap between the two energy levels of electron transition. Right? Energy of the photon is equal to energy gap between the two energy levels of transition, electron transition. So that energy is marked here. So you see, as energy gaps increase gradually, right? Energies of the spectral lines will also increase gradually, right? Okay, no? Right? Let's mark this stuff, right? Let's this in, right? So when the electrons are coming towards n equals 1, these are the transitions responsible for Lyman series, electron transitions responsible for Lyman series. Right? So these are the electron transitions responsible for Balmer series. Balmer series. This is the Balmer series, right? These are electron transitions responsible for Balmer series, right? The idea is clear? Right. So if the electrons are coming towards n equals 3 from higher energy levels, from those energy photons released, from those energy photons released, right? The partition series lines has been originated. Electron transitions responsible for partition series. Right? No? Like that, when the electrons are coming towards n equals 4 from higher energy levels, is the reason for the bracket series. And when it comes to n equals 5, those transients are responsible for the fund series. Right? These are transitions bracket fund series. Right? The home of the high energy spectrum is bogian. Is very clear, right? The me wage n equals 1 වලට electron transit දෙද්දි Lyman හැදෙනවා. හරි. වගේම වගේ n equals 2 වලට එද්දි electrons. Because 2 වලට electrons transit වෙද්දි like this. High energy levels වලින් n equals 2 වලට එද්දි බාම හැදෙනවා නේද? n equals 2 වලටදී බාම හැදෙනවා. n equals 3 වලට හොර වෙනවා නම් partition හැදෙනවා. ඒ විදිහට තමයි series of lines obtain වෙන්නේ කියලා. Right? Nesbo පැහැදිලි කරන්න. Right නේද? හරි ඕක තමයි high energy spectrum එකේ right origins පැහැදිලි කරන විදිය. හරිද? අපි පොඩ්ඩක් මේ engineer diagram එකත් එක්කම before we going towards before we drawing this stuff, right? තව පොඩ්ඩක් මේ දින patterns ටික මේ diagrams එක පැහැදිලි කරගන්න try එකක් දෙමු. හරි. දැන් අර මං කිව්වා ඒක copy paste කරන්න පුළුවන් වෙන්නේ ඇයි කියලා. ඒ කියන්නේ මෙයාගේ second line onwards ගත්තට පස්සේ ඒක copy paste කරමු මෙතනින්. ඔයාලට බාම series එකේ gaps ටික කොහොමද එන්නේ කියලා පොඩ්ඩක් කතා කරමු. හරි. මේ third line onwards තරම් copy paste කරොත් partition series එකෙන් gaps ටික කොහොමද එන්නේ කියලා පොඩ්ඩක් කතා කරමු. මේකෙන් explain කරගමු. පුළුවන් නේද? ඔන්න බලන්න. The gap between the first and second line, sorry, gap between the second and third line of the Lyman කියලා කියන්නේ. The gap between the second and third line of the Lyman means the second line is the third line. That means actually this gap නේද? ඒ කියන්නේ මෙන්න මේ gap එක නේද ළමයි? ඇයි? එහෙම කියන්නේ. The second line එකේ energy කියලා කියන්නේ මොකද්ද? second line එකේ energy කියලා කියන්නේ this. The energy of the second line is equal to the difference, the gap between the right energy levels of transition. So energy of this photon, energy of the second line means this photon. Energy of the second line means use this second line. This is the second line. This is third line. Energy of the second line means the photon released here. Photon released here. Its third line means the photon released here. හරි. එතකොට මේ ෆෝටෝන් එකේ මෙතන රිලීස් වෙන ෆෝටෝන් එකේ අතර එනර්ජි ગેප් එක කියලා කියන්නේ එනර්ජි ඩිෆරන්ස් එක කියලා කියන්නේ මේක නේද? Photon released here when the electron comes from here to here, the photon released is carrying some energy related to this energy gap. හරිනේ? මෙතනට ෆෝටෝන් එකක් එද්දි හරි ඒ ෆෝටෝන් එකේ එනර්ජි එක සමාන වෙනවා මේ එනර්ජි ගැප් එක. එනර්ජි ගැප් of the electron transition occurs. හරි? ඒ වගේ මෙතනට ඉලෙක්ට්‍රෝන ෆෝටෝන් එකක් එද්දි එතන එනර්ජි එක සමාන වෙනවා මෙතන තියෙන එනර්ජි ගැප් එක. මෙතනට ෆෝටෝන් එකක් එද්දි ඒකේ එනර්ජි එක සමාන වෙනවා to this energy gap. අර මේ එනර්ජි ගැප් එකයි මේ එනර්ජි ගැප් එකයි අතර ඩිෆරන්ස් එක තමයි ඒ ෆෝටෝන්ස් දෙකේ එනර්ජි ඩිෆරන්ස් එක කියලා කියන්නේ. That is this much, that is this much. එතකොට මේ එනර්ජි ෆෝටෝන් එකේ මේ එනර්ජි ෆෝටෝන් ඩිෆරන්ස් එක කියලා කියන්නේ ඔය මම මාක් කරපු එක. මේ ඩිෆරන්ස් එක කියලා කියන්නේ මේක. මේ එනර්ජි ඩිෆරන්ස් එක. ඒ එනර්ජි ඩිෆරන්ස් එකම නේද තියෙන්නේ පළවෙනි ෆෝටෝන් එකේ දෙවෙනි ෆෝටෝන් එකේ ලයිමාන්ගේ sorry බාමගේ පළවෙනි ෆෝටෝන් එකේ බාමගේ සෙකන්ඩ් ෆෝටෝන් එකේ බාමගේ පළවෙනි ෆෝටෝන් එකේ සෙකන්ඩ් ෆෝටෝන් එක අතර තියෙන එනර්ජි ගැප් එකත් ඒ ගැප් එකම නේද? same gap නේද? तोर मेयाई सेकंड फोटोन के थर्ड फोटोन अतर दिन गैप එකම තමයි एनर्जी गैप එකම තමයි मेयाई फर्स्ट फोटोन එකේ सेकंड फोटोन අතර තියෙන एनर्जी गैप එක difference එක because we are considering the same gap right same two gap between the energy gap between the two same energy levels we are considering that හරිද ඉතින් ඒතර බාමගේ second and third gap එක කියලා කියන්නේ බාමගේ second photon එකයි third photon එක අතර energy gap එක කියලා කියන්නේ මෙන්න මේක. මෙන්න මේ gap එක. ඔය gap එක සමාන වෙනවා මෙයාගේ third photon එකයි මෙයාගේ fourth photon එක අතර energy gap එක. third photon fourth photon අතර energy gap එක කියන්නේ ඕක. तो थर्ड फोटोन ने फोर्थ फोटोन ने एनर्जी गैप එකට සමාන වෙනවා බාමගේ सेकंड फोटोन थर्ड फोटोन ने दिस गैप ඔක සමාන වෙනවා මෙයාගේ थर्ड and fourth फोटोन्स වල එනර්ජි ගෑප් එක මෙතනට හරිද පැහැදිලි ඒ විදිහට කොපි පේස්ට් කරන්න පුළුවන් අපිට මෙයාගේ වැඩෙත් ඔය විදිහම හරි see the things are clear shape හරි එහෙනම් පොඩ්ඩක් මේ ටික අද ගන්නවද මුලින්ම ionization spectrum කියන එක තමයි මෙතන මේක අඳින්න ඊට පස්සේ energy level diagram කියන තැනට මේ පින්තූර අඳ ගන්න right පොඩ්ඩක් මේ pictures ටික දාගන්න ළමයි හරි okay නේද මම මේක පොඩ්ඩක් clear කරන්න explanations වලට draw කරපු ටික අයින් කරන්න right හරි complete කරගන්න ඕලම just draw the pictures there two diagrams Okay. Right now, just draw these two diagrams. Now, when drawing this one, I explain that thing later, right? But when drawing this energy level diagram, you have to maintain this pattern. What is that pattern? This one. So first draw the first n equals 1. First draw the n equals 1. Then just draw the n equals infinity. මුලින්ම n equals 1 එක draw කරන්න ඊට පස්සේ n equals infinity එක draw කරන්න. ඊට පස්සේ n equals 2 draw කරද්දී අඳිද්දී right, just take the center between the n equals 1 and the infinity and draw this n equals 2 bit above that center, bit above that center. ඒ කියන ළමයි n equals 1 draw කරා n equals infinity draw කරා ඒ දෙක අතර center එකට වඩා පොඩ්ඩක් උඩින් තමයි n equals 2 එක අඳින්න ඕනේ. In other words, the gap between the n equals 1 and n equals 2 should be greater than the gap between the n equals 2 and n equals infinity. n equals 1 and 2 අතර තියෙන gap එක වැඩි වෙන්න ඕනේ ළමයි n equals 2 and infinity වලට වඩා. right, අන්න ඒ විදිහට තමයි මේක අඳින්න ඕනේ. right, then drawing the n equals 3, you have to maintain a greater gap between the n equals 2 and 3 than the 3 and infinity. හරි, එතකොට n equals 3 එක අඳිද්දී මුලින්ම 2 infinity වල තියෙන මැද තියෙනවනේ. එතනට වඩා පොඩ්ඩක් උඩින් n equals 3 එක අඳින්න. So that maintaining a greater gap between the n equals 2 and 3 compared to the gap between the 2 and infinity. Sorry, 3 and infinity. 3 and infinity වල gap එක 2 and 3 වල වැඩි වෙන්න ඕනේ. ඒක maintain වෙන්න ඕනේ ළමයි when drawing the energy levels of the diagram. Why I am saying so? ඇයි මම එහෙම කියන්නේ? Right? It is like this. So gap between the n equals 2 and 1 means the Lyman's first line. Means that is responsible for the energy of the Lyman's first line. This one. Gap between the 2 and infinity. 2 and infinity means that is responsible for the Balmer's ultimate line. Electron is coming towards the n equals 2 means it's a Balmer line. Coming towards n equals 2 means it's a Balmer line. But that is the Balmer's ultimate line, the final line. If it is coming from the n equals infinity. If that electron is coming from the n equals infinity towards the n equals 2, that is going to be the Balmer's ultimate, the highest energy line possible. Right? So we can clearly see the Lyman and Balmer series can be observed as two separate spectral series. මේ දෙක separated spectral series දෙක. ඒ කියන්නේ Lyman ගේ first line එකේ energy එක වැඩි වෙන්න ඕනේ Balmer ගේ last line එකේ energy එකට වඩා. As Lyman and Balmer can be seen as two separate spectral series, the Lyman's first line should have a greater energy than the Balmer's last line. That means the gap between the 2 and 1, which is responsible for the Lyman's first line, should have a greater gap compared to the gap between the infinity and the 2, which is responsible for the Balmer's last line. Lyman's first line should have a greater energy than the Balmer's last line. So gap between here to here, 2 to 1, should be greater than the gap between the infinity and the 2, which is the Balmer's last line. This is the Lyman's first line. Lyman's first line appear at a greater energy than the Balmer's last line. Alright? As we observed to Lyman and Balmer series as two separate sister series. Right? එහෙනම් ඒ විදිහට maintain කරගන්න. එක ඇඳ infinity එක ඇඳ දෙක අඳිද්දි පොඩ්ඩක් අර half එකට පොඩ උඩින් අඳින්න. third එක අඳිද්දි දෙකයි infinity අතර half එකට පොඩ උඩින් අඳින්න. Like that you have to maintain that thing. So you will ultimately see, right, the gaps, right, CVLE comes closer to each other among the energy levels as well. Right? Just complete this stuff. First draw this one and this one. No need of drawing these two. මේ දෙක අඳින්න ඕනේ. Right? මේ ටික අඳින්න. These energy levels are referred to as quantum numbers. The first energy, second energy, like that. N values, quantum numbers, and energies of them are also indicated. Right? I'm telling my minus values is the energy indicate where the n equals infinity coming up with zero energy. With that convention, they have assigned the energies as minus, right? So මෙතන පොඩ්ඩක් ලියන්න මේ Lyman seeds ultraviolet region, and you can write like this: due to electron transitions towards n equals 1 Lyman BAM, electron transitions towards n equals 2. Partial top theme ලියනවා due to electron transition towards n equals 3 like that. Make it towards n equals 4 and front towards n equals 5. Right? Just complete this stuff. right නේ හරි ඉතින් පැහැදිලි අපි එහෙනම් මේ කතා කරපු දේවල් describe කරලා පිළිවෙලට ලියා ගමුද right okay let's go to the next page lama there the things are appearing what we have discussed see some important facts on hydrogen emission spectrum that is mentioned right see what they are saying right hydrogen atomic spectrum is a result of electron transition to lower energy levels of excited hydrogen atoms right excited hydrogen atoms වල electrons lower energy levels වලට transit වෙද්දී ඒකෙන් release වෙන photons වලින් තමයි මේක hydrogen spectrum එක originate ලා තියෙන්නේ right then it says in hydrogen atom there should be energy levels in hydrogen atoms there should be energy levels and they are named as n equals 1 2 and n equals 3 right in hydrogen atoms there should be energy levels right to observe this that should be there right and those are named as n equals 1 2 3 and 4 these n values are introduced by Niels Bohr just fill that blank in red color in here Niels Bohr introduced by Niels Bohr and they are called as principal quantum numbers these are called as principal quantum numbers right principal quantum numbers right principal quantum numbers right these are principal quantum numbers that is red color principal quantum numbers right okay next what it says when an electron falls from an initial energy level to a final energy level a photon is released the energy of that photon is equal to the energy gap between the corresponding energy levels okay let's write this thing මේකත් දාගන්නකො so it's like this let's say an electron is coming from this kind of high energy level to a low energy level like this is the initial value the final energy level E initial and E final right what it says when an electron is coming from an initial energy level to final energy level some energy photon is released electronic wave is released E photon is released right so actually we can come up with the energy of this photon we can calculate this energy of the photon by considering the energy gap between the two energy levels of electronic transition මතකයි නේද අර මේක නිකන් 30 joules නම් මේක 10 joules නම් photon energy කීයද 30 minus 10 20 joules so this photon energy is equal to the energy gap delta E between the two energy levels of transition 30 minus 10 හරි ඒක තමයි කියන්නේ so we can write it as right this E photon is equal to delta E photon is equal to delta E right just write this at this space just draw this diagram and write this thing so E photon can be considered as h mu right so h mu is going to be equal to delta E then you get one can say EI minus EF or one can say in terms of lambdas it is going to be HCO lambda this is the energy gap the positive value is considered right so by considering the energy gap between the two energy levels of electron transition right we can come up with the energy of the photon we can come up with the energy of the photon as well as frequency of the photon as well as the right the wavelength of the photon හරිද by considering the energy gap between the two energy levels of electron transition we can come up with the energy of the photon frequency of the photon or the wavelength of the photon by equaling that energy to the energy gap of electron transition. Alright. So just complete this one. Just draw this diagram and at the other side, just write these two. Alright. Right. That is done. Next point. It says the first four lines observed in the hydrogen spectrum belongs to the wavelength of 656 nanometers, 486 nanometers, and 436 nanometers, and that thing, right? And these spectral lines are due to electron transit towards n equals to. මුලින්ම observe කරපු spectral lines එක තමයි මේ හතර. මොකද visible region lines කොහොමත් මුලින්ම observe වෙනවා. That is what we see from our naked eye. So basically, to observe these things, we need to come up with some advanced equipment, advanced spectrometers. But even with the naked eye, we can observe the colorful lines here, which is appearing in the visible region. Right? So these are the first four lines observed at the hydrogen emission spectrum. Those are colored lines, right? Coming under the Balmer series, right? Balmer is the one who observed those things, right? The red, green, blue, and violet lines, right? So those are due to electron transition towards n equals 2. We had seen that, right? Okay. These series of lines is called the Balmer series, and those wavelengths belongs to visible region of the electromagnetic spectrum. මේ අපි Balmer series එක කියලා කියනවා. ඒක visible region එකට තමයි වැටෙන්නේ electromagnetic spectrum එකේ, right? ඔයගේ electromagnetic spectrum එකේ visible region එකේ lines එකක් තමයි මේ Balmer series එකේ ඉන්නේ. ඒක තමයි ඒගොල්ලට colors තියෙන්නේ. Right? Okay, some space is there. So let's come up with those data there. Data ටික පොඩ්ඩක් කතා කරමු එහෙනම්. Space එක, right? So you can write these things, right? All right. මේක ලියන්න ළමයි. Name of spectral line, color, and electron transition. So we have H alpha, H beta, H gamma, and H delta. Colors, H alpha is red in color. Red part line පාට කරගන්න. This is green, it's blue, violet. And electron transition towards. So basically, Balmer series means always those electron transitions should be towards n equals 2. Balmer series ne අනිවාර්යෙන් n equals 2 වලට electron එක transit වෙන්න ඕනේ. Balmer series of lines. So the first line of the Balmer means it is coming from the nearest energy level to the n equals 2. That means from the n equals 3. Next line is from the next nearest. N equals 4. N equals 5 from here. This line from the n equals 6 like that. That is how the electron transitions are written. So you see, this from n equals 3 to 2, this from 4 to 2, 5 to 2, and 6 to 2. See, this from 6 to 2, right? Just complete this table now. Just color this stuff, right? Red, green, blue, and violet. Right, no? Okay, let's complete this up. Right. Next one. At the next page it says With time, few other spectral line series also identified. With time, few other spectral line series also identified. Right? That means Lyman, Paschen bracket found was also identified. Right? Let's come up with those things. Right? We got mention karagam. All right. So name of series, electron transition towards and region of electromagnetic spectrum. Right? Name of series, Lyman, Balmer, Paschen, bracket, fund. Electron transition units, Lyman is when electrons are coming towards n equals 1. From those emitted photons, Lyman is observed. Towards n equals 2 for the Balmer, it is 3 for the Paschen, and coming towards n equals 4, the bracket observed. Fund series of lines observed when electrons are coming towards n equals 5, right? So region of spectrum, right? Lyman coming under the UV, Balmer partially visible. So one can say UV as well as visible. First 4 lines visible, and the next line is coming under UV. And these 3 spectral series come under the IR region of electromagnetic spectrum. Alright, පොඩ්ඩක් මේකත් අපි ලියගමුද? Complete this table. Right. Let's complete that. Right now. Okay. Next point. It says, when considering series of lines of any individual series, these are the observations, main observations, right? When considering series of lines of any individual series, that means when considering series of lines in any individual series, like this, with this one, with this one, you see, going towards higher energy region, the gaps between the spectral lines decrease, or lines become closer to each other when going towards higher energy region, right? Let's write that thing. Let's write there. Gap between spectral lines, gap between spectral lines, gap between spectral lines decreases. Gap between spectral lines decreases. Gap between spectral lines decreases with the increasement of frequency. With the increasement of frequency. With the increasement of frequency slash energy. With the increasement of frequency slash energy. Right now. Okay. At the next line, come to the normal color and write. This must be due to, 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 put a comma and write it in red color. Just come up with the reason, right? This must be due to, come to red color and write. Energies of energy levels, energies of energy levels, energies of energy levels becoming more closer, becoming more closer, becoming more closer, energies of energy levels becoming more closer when going from n equals 1 to n equals infinity. N equals 1 to n equals infinity. You see? When going from n equals 1 to n equals infinity, energies of energy levels becoming more closer. When going from n equals 1 to n equals infinity. Right, no? That is the idea. Okay? Right. Next point. What it says? See? The note, right? It says, the gap separating each series will decrease. Gap separating each series means this thing, right? The gap separating each series will decrease going towards lower energy region. This is the high energy region. This is going towards lower energy region. The gap separating each series will decrease. This is also mentioned, right? So ultimately, bracket and fun series get overlap. Bracket and fun series get overlap. No gaps between those series. Bracket and fun. Got the idea? Right. Next one. The ionization energy of hydrogen atom. Okay, let's discuss a bit about the ionization energy. What this ionization energy means? Ionization energy of hydrogen atom. Let's discuss. What that means, lamai? Ionization energy කියන්නේ කියන්නේ මොකක්ද? What it meant by ionization energy? Ionization energy කියන්නේ මොකක්ද? Right? Ionization energy means the minimum energy needed to eject an electron from a gaseous atom to form the 1 plus gaseous sign. This is ionization energy. The minimum energy needed to eject an electron from a gaseous atom to form the gaseous 1 plus ion. That is ionization energy. Ionization energy කියන්නේ gaseous atom එකකට supply කරන්න ඕන minimum energy එක, අඩු energy එක. එයාගෙන් electron එකක් eject කරලා electron එකක් අයින් කරලා gaseous ion එකක් හදන්න. gaseous atom එකකින් electron එකක් අයින් කරලා gaseous ion එකක් හදන්න. supply කරන්න ඕනේ minimum energy එක තමයි ionization energy එක. Right? Hari. So that means if you are considering the hydrogen atom, the hydrogen atom electron is here. The hydrogen's electron. So I am coming up with this energy level diagram. It like this. Right? Let's consider the energy level diagram here of the hydrogen atom. So this is kilojoules per mole, right? Energy. Here the zero applies, the zero energy. Here cells are there. So what is ionization energy? Ionization energy means, so normally the hydrogen atom is with some electron with here. No? In hydrogen atom the electron is here. Or common hydrogen atom electron is here. Alright. So the ionization energy මොකද්ද? The minimum energy you need to supply to get this electron from that. So electron එක මෙන්න මෙතනට excite කරන්න පුළුවන් මෙතනට. මෙන්න මෙතනට. excite කරන්න පුළුවන් එක තමයි ionization energy කිය. If you are to put this electron to here, then the electron will be emitted from the atom. මොකද මෙතනින් එහාට ළමයි energy levels නැහැ atom එකේ. electron එක මෙතනට excite කරාට electron will occupy one of the energy levels of the atom. If you excite the electron to here, it will occupy one of the energy levels of the atom. If you are excite the electron to here, it will occupy one of the energy levels of the atom. So that means electron is inside the atom yet. If you are to put this electron to here, මෙතනින් එළියට දාන්න පුළුවන් නම් මෙතනින් එළියට දාන්න පුළුවන් නම් then electron won't occupy any of the energy levels of the atom. That means electron is out of the atom. So the minimum energy you need to get rid of this electron from the atom is actually this value here. මෙතන තියෙන value එක. දැන් මෙතන try එළියට දැම්මොත් කොහොමද electron එක atom එකෙන් එළිය. ඔය supply කරන අඩුම energy එක. ඔය supply කරන අඩුම energy කියලා කියන්නේ electron මෙතනට transit කරන්න දෙන්න ඕන energy එක. Actually, that energy is related to what? That energy is related to the energy gap between the n equals 1 and the n equals infinity. Your ionization energy is equal to the energy gap between the n equals 1 and the n equals infinity. So actually, that means that energy gap, the n equals 1, the energy gap between the n equals 1 and infinity, that is actually equal to, that is responsible for the Lyman's last photon. Lyman's last photon. When an electron is coming from n equals infinity to n equals 1, when an electron is transit from n equals infinity to n equals 1, that is where the Lyman's last line occurs. That is the energy of the Lyman's last line. So that is related to this. So Lyman's last line is responsible for the energy gap එකක්. The energy gap between the n equals infinity and the n equals 1. ඒ වගේම ionization energy එකට involved energy gap එකක්. The energy gap between the n equals 1 and infinity. So actually Lyman's last line, that energy represents your ionization energy. The energy of the Lyman's last line represents your ionization energy, which is the energy gap between the n equals 1 and the infinity. හරිද? එහෙනම් ඔයාලට hydrogen atom එකේ ionization energy එක හොයාගන්න පුළුවන්. මේ Lyman's last line එකේ energy එක දන්න ඕන. එහෙනම් තමයි Lyman's last line එකේ frequency එක හරි lambda හරි දන්න ඕන. If you know the frequency of this thing, the energy of the photon can be calculated by using the h-mu. Or if you know the lambda of this line, the energy can be calculated by using the HCO lambda. So if you know the energy, or the frequency or the lambda of the Lyman's last line, then you can calculate the ionization energy. Right? හරිද? එහෙම නැත්නම් if you know the energy gap between the n equals 1 and the infinity, then also you can calculate the ionization energy. Right? ඒ ක්‍රම දෙකේ hydrogen atom එකේ ionization energy එක ඔයාලට හොයාගන්න පුළුවන්. හරිද? හරි අපි එහෙනම් ඔක ලියමුද? Right? So it is there. So the ionization energy of hydrogen atom, energy needed to supply to eject an electron from hydrogen, is given by, it is written, energy gap between n equals 1 and infinity energy levels. This means the ionization energy relates to, right, n equals infinity to n equals 1 transition, and so that the highest energy line in Lyman series. The highest energy line in Lyman series, Lyman's last line. So let's have some note there. To note that down then. Idea go liya ganna. Let's copy some note there. Note that down. If energy level diagram is given, right? Energy level diagram dila diyana me wage. N equals 1, we have to consider n equals 1 and then n equals infinity, right? E infinity, E1, right? So ionization energy means actually you need to provide some energy. Provide some energy, maybe as photon, right? To eject this electron to here, to transfer this electron to here, right? To transfer this electron to here, you need to provide some energy. So this is referred to as the ionization energy. This energy required is referred to as the ionization energy. electron මෙතන transfer කරන දුන්න energy එක තමයි කියන්නේ ionization. Right? So we can write the photon is equal to delta E. So one can say now the ionization energy is equal to delta E. Delta E means here the gap between the 1 and infinity. Right, 1 and infinity. So you can apply the numbers here. So normally 1 hydrogen Ag1 coming from with 13 kilojoules mole is coming up with 0. E infinity is equal to 0. So the gap 0 minus kilojoules mole, that is going to be 100,002 kilojoules mole. This is the ionization energy of the hydrogen atom. By concerning the gap between the infinity and 1, you can come up with the ionization energy, right? This 0, so this is 1, 3, 1, 2, this is 0. Right? So that is how you are supposed to come up with the ionization energy if the energy diagram is given. So the other way around is if the spectrum is given. If the spectrum is given, then what you need to do? If the spectrum is given, then what you need to do? Right? So first of all, you have to consider the Lyman series. First, you need to consider the Lyman series. Right? Lyman series coming up like this. And then you have to consider the last line of Lyman series. Consider the Lyman series and last line. That means highest energy line. Last line on the highest energy line. So I'll write this last line. So highest energy line, right? Right? Consider its lambda. Consider its lambda. That is going to be the Lyman's smallest lambda. Or consider the frequency, Lyman's highest. Right? Consider the Lyman's lowest lambda or the highest frequency, that means highest energy. Consider that line, and then that will lead you to the ionization energy. Right? So E photon, the E is delta E. That photon, right? So ionization energy equals delta E. No? Photon of Lyman last line. No? So applying this, we will come up with IE ionization energy is equal to H mu photon is photon can be written as H mu highest of Lyman or ionization energy is equal to lowest of Lyman, lambda lowest. Okay, so let's complete this stuff. This is how we are supposed to come up with the ionization energy of the hydrogen atom by considering the last line of the Lyman series, by taking its frequency of the lambda. Let's complete this stuff. Right now, okay. Right. Let's consider the next one appearing in your note. It is said the other single electron systems will also give atomic emission spectra like hydrogen atomic spectrum. Right. Other single electron systems also give some hydrogen atomic spectra like hydrogen atomic spectrum. That is what it says. Right. See what is that idea is. Right. Okay. So it says, right, some other atoms, right, also when they are coming up with single electrons, that means basically ions, not the atoms, no? So when considering helium plus, right, or when considering lithium 2 plus, the helium is with 2 electrons. Helium plus means just 1 electron is there. 1 electron is removed from 2. Lithium is with 3 electrons. Lithium 2 plus means 2 electrons are removed. That means just 1 electron there. Right? When considering single electron systems like that, right? When considering single electronic systems, those are coming up with some spectra with the similar pattern. Some spectra with similar pattern, but those are not identical. Remember that. See what it says. So if you are considering hydrogen atom, and if you are to think of n equals 1 series of hydrogen atom, example, let's say n equals 1 series, right? Let's say consider n equals 1 series. So if you are to see this trend appearing like this, is how the line mass looks like with the hydrogen atom. N equals 1 series. Going towards higher energy region, spectral lines become more closer to each other, right? And is named as Lyman for the hydrogen atom. So this statement says even the helium plus as well as the lithium 2 plus, which are single electron systems, the statement says these will also come up with some spectra with similar pattern. Then going towards higher energy region, the lines become more closer to each other. See? But remember one thing. Similar pattern. Going towards higher energy region, lines become closer to each other. But the spectra are not identical. Identical means you can't apply this helium plus spectrum on top of the hydrogen atom. These are not going to overlap. If you apply the helium plus spectrum on top of the hydrogen atom, the two spectra are not going to overlap with each other. If the overlap occurs, that means those are identical. But here the things are not identical. If you have to apply the lithium 2 plus on top of the hydrogen, the things are not get overlapped. And even though the pattern is same, not identical. The frequencies are different. The first line of appearing at here, but here, you see, few different frequencies. Even though pattern is same, the frequencies of lines are different, not identical. For these, no name is there, right? Only the hydrogens series are known as Lyman, Balmer, Paschen, and Brackett. Fun. Not the spectra series of other single electron systems, right? So only the n equals 1 series of hydrogen is known as the Lyman, not the others, right? Right? So you can come up with this thing. Just draw this one, and then you can write same pattern but not identical. But not identical. That means wavelengths, frequencies of spectral lines differs to that of hydrogen spectrum. That is what we say, that these are not identical. Right? Let's complete this up. right nela hari inala godak podi questions එක තුනක් කරමුද මේකේ. Let's do few questions, and then only you will get the complete idea here with the hydrogen spectrum and the level stuff and the electron transitions, right? hari එහෙනම් podi question එකක් දැක් කරමු. බලන්න වාගේ tute එක අපි questions ටික බලමු. Right, just do few of the questions appear in there. Hard. Yeah, the question number 1. See, question number 1. See what they are saying. The first line of the Balmer series is at 656 nanometer wavelength. Calculate the energy gap between the two energy levels corresponding to that line. This is about the first line of Balmer. So basically, that is due to an electron transit from n equals 3 to n equals 2. First line of Balmer. Balmer line means electron should come towards n equals 2. Balmer line means electron should come towards n equals 2. Balmer line marks towards n equals 1. Balmer means n equals 2. Right? So the first line means it should come from the nearest energy level to the n equals 2. That means from the n equals 3, the electron is coming, right? So when this electron transition occurs, kind of energy photon will release. Right? If this is the E3, this is the E2, the energy. So energy of this photon is equal to the energy gap, or the energy gap between the 1 and 2, sorry, between 3 and 2 is equal to the photon of energy released. Electron මෙතන දෙද්දි හරි අනිවාර්යෙන් energy සමාන to the energy gap of the two corresponding energy levels. So E photon can be written in terms of wavelengths. This guy's wavelength is given 656 nanometers. So we can come up with the energy of the photon in terms of now as we know the lambda. So what is the equation relates the energy and the lambda? That is 𝐓𝐶O lambda. 𝐓𝐶O lambda is the equation relates the energy and the energy of the photon and the lambda. So these are constant values. So we can apply the lambda to come up with the energy of the photon. That is equal to the energy gap between the two energy levels. So H Planck constant, it is 6.6 into 10 to the power minus 34 joules per second. C is the light speed, that is 3 into 10 to the power 8 ms minus 1. O lambda, lambda is 656 nanometers. Nano means 10 to the power minus 9 meters. Last day we had discussed these things, right? These are some right known calculations now. We had done those things last time. Okay, so we can take this one as 660. We can take this one as 660, right? So it is 660. So let's simplify this one. This can be written as 6.6, the numbers 3, and you can take this as 660. 10 to the powers minus 34 is there, plus 8 is there, and this minus 9 comes to the top as plus 9, right? So this is like I am dividing by 6.6, 1 of 6.6 and 100 of those, right? So another 2 comes to here. This 100 comes to top as minus 2, right? 10 to the power 2 comes as minus 2. So now you have some 3 here, some 3 here, and 10 to the powers minus 34 minus 36 and plus 17, minus 36 plus 17, so that is minus 90, minus 90 to the power minus 90. So this unit can be used as your substitution is done in SI units. The answer comes in SI units, that is joules. Right? This is just rough work. Right now, this is how we are supposed to come up with the answer of the question number 1. Just complete this rough down. Right? Hi. Let's come up with the second question. Question number 2. Question number 2. First part 1 A. See what it says. Consider the following energy levels in an atom. Okay. Calculate the energy of the photon required to excite an electron from E2 to E3. So, excite an electron from E2 to E3, no? Right, from E2 to E3. So, first consider the energy level diagram here. So, you have electron at E2, n equals 2, you have electron, and you have to excite that into E3 towards n equals 3. To do this electron transition, definitely you have to supply the energy to the electron as an energy photon. To do this transition, you have to supply the energy as an electric photon to increase the energy of the electron. So here with the E2 you have a lower energy. Here with the E2 you have a lower energy, minus 10. With E3 you have a great energy, minus 5. So you need to increase the energy of the electron. For that, you have to supply some energy in the form of photon. So what is what equation, what relationship we are going to apply? So E photon is equal to delta E, energy gap between the two energy levels of electron transition, delta E between 2 and 3, right? Okay. So the energy gap, see the gap between these two. When taking a gap line, always deduct the lower value from the higher value. Deduct the lower value from the higher value. So this is the higher value. Higher value minus lower value. So minus 5 plus 10, PV5. No? So this is the energy of the photon needed to excite an electron from E2 to E3. Right now? Okay. Right now? When you need to increase the energy of an electron, you need to supply some energy to the electron. When the electron is coming to a lower energy level, when the electron is releasing energy, some E photon will be released. But here it is needed to gain some energy to come to a high energy level, so that the energy should be supplied as water. Right. The part B. Let's complete part B. Is clear? Simple stuff. Next up. Calculate the wavelength of a photon which is required to excite an electron from E1 to E4. Right? With the part B, you are supposed to excite an electron from E1 to E4. So what kind of a process we are supposed to do now? So you have electron at n equals 1, E1 energy is there with the electron. To occupy that energy level, the electron should have the energy corresponding to the energy level, right? So we need to excite that into fourth energy level, to E4. So we have to increase the energy of the electron to minus 1 into 10 power minus 19. We have to increase the energy of that electron. So for that, we need to use the energy, provide some energy to the electron as an energy photon. So the relationship is the energy of the photon is equal to the energy gap between the two energy levels of electron transition. Here 1 to 4. Right? So in this case, we need the answer in terms of wavelength. So the energy of photon can be related to the wavelength with the use of 𝐓𝐶O equation. Right? So that we can come with the wavelength of the photon now. So any difference between the two energy levels. So this difference is what? 15 is there, 1 is there, the difference is just 14 is, no? Let's apply that value. The difference, right? That is 14 into 10 to the power minus 19 joules. The difference. So H is 6.6 into 10 to the power minus 19, minus 34, no? Joules per second. C is 3 into 10 to the power 8. M is minus 1. Lambda, that is what we require to find. This value is 14 into 10 to the power minus 19 joules. So we need to come with lambda. Let's do the simplifications here. So if you subject the lambda, it's going to be some 6.6 is there, some 3 is there, that 14 comes to bottom. In power values, minus 34 plus 8 is there, and when that minus 19 here come to the top as plus 19. Right now? Okay. Right. So this is like 19.8 divided by 14 into 10 to power plus 19 and 8 plus 27 minus 34, that is minus 7. So let's simplify this thing. It is 19.8 divided by 14, 1.41. So this thing is actually 1.41 into the power minus 7. Right? So this is the rough work, right? So the lambda is equal to 1.41 into 10 to the power minus 7 in meters, right? In SI units, right? As your substitution is done in SI units, always the answer comes in SI units. Right now? Okay. Just complete this off. Right. Next one. Let's come up with the part C of the question number 2. Right. Part C. See what they are referring to. Calculate the frequency of the photon which will be emitted when an electron comes from E3 to E1. Right? Electron comes from E3 to E1. E3 to E1, right? So electron transition occurs between the E3 and E1. Electron is coming from E3 to E1. So E3 carries some great energy, E1 carries some low energy. Minus 15 is a smaller value than the minus 5. So that electron has to remove the excess of energy when he is to reside, occupy a low energy level, low energy. So that the excess of energy will be released as a E photon, photon of energy. Right? When electron occupies this energy level, it is with this energy. When electron occupies this energy level, it is with this energy. So the excess energy should be released as a photon. Right? So they are asking us the frequency of this thing, frequency of this photon. We need to come from here to here, the release photon. Right? So we can come up with the same relationship. Energy of the photon is equal to the gap between the two energy levels of electron transition. Right? Now we need the answer in terms of mu, the frequency. So we can relate the photon's energy to the frequency by using the E is equal to h mu. So h mu is equal to the energy gap. The energy gap between the two is what? That is equal to the gap between these two. Right? Yeah. 5 and 15. That is 10. That is the gap, energy gap. Right? So that is equal to minus 19 joules. So h is the Planck constant, 6.6 into 10 to the power minus 34 joules per second. Mu, that is what we need to find, and this is 10 to the power minus 19. So let's simplify the stuff. So mu is equal to 10 is there, 6.6 is there, and 10 to the power minus 19 is there. This 34 comes to top as plus 34. This 34 comes to right. This 34 comes to bottom, and that can be taken to the top as plus 34. Right? So 10 divided by 6.6. What will be that value? That is 1.51. So this is 1.51 into 10 to the power minus 19 and 34. That is minus and plus 34. That is plus 15. No? So mu is equal to 1.51 into 10 to the power plus 15. So this time it says, or one can say it's minus 1. Right? Both are acceptable, right? As I said it, both are acceptable. Per second or hertz. As long as your substitution is done in SI units, the answer comes up in SI unit. Right? No? Let's complete that question. Right. So the last question. Last one. Question number 3. Let's do the stuff. Right. Question number 3. See what it says. X-rays emits when highly energized cathode rays hit a copper metal target. Right? Wavelength of those X-rays is given. Calculate the energy of 1 mole of these X-rays photons. So what they are saying? X-rays emit when highly energized cathode rays hit copper metal targets. Right? So when you have copper metal targets, copper anodes, right? When those cathode rays hit and transfer their kinetic energies, right, to the electrons in the copper metal, those electrons will get excited. Right? Those electrons will get excited. Electrons will get excited by the cathode ray kinetic energy. Will get excited. Right? After some time, those electrons will come back to the original energy level, original ground state. So let's say this is the ground state, the low energy level, this is the excited state, high energy level. Right? When these electrons comes back, the excess of energy will be released as an energy photon. In this case, which is happening at the X-ray region. X-ray photon will be released. So what they are asking is, calculate the energy of 1 mole of these X-rays. Energy of 1 mole of these X-rays. That is what they are asking. Right? That is what they are asking. Right? Right. So and they are giving us the lambda of this thing as well. So they are asking for energy of 1 mole of photons. So this is regarding energy of 1 mole of photons. 1 mole of photons. So that we have to use the E is equal to NH mu or NHCO lambda. As lambda is provided, better to go up with the relationship with the lambda. For more than one photon, that means NHCO lambda. Right? So let's apply the values. N means the Avogadro number, 1 mole. H is 6.6. C is 3 into 10 to the power minus 8. So in power 8. Light speed. Right? Lambda is given as what? 0.15 nanometers, right? Nano means 10 to the power minus 9 meters. Let's simplify the stuff. So you have some 6 here, right? 6, this can be taken as 6, right? Is 6.6. 3 is there, 0.15 is there, 10 powers 23 is there, minus 34 is there, plus 8 is there, minus 9 comes to top as plus 9. Right? That's all. So this is like we can simplify this stuff, right? 1 3 is there, so this is just 0.05, no? So let's simplify stuff. 6 into 6.6 divided by 0.05, 792 into 10 to the powers 23, 31, 40 plus 40 and minus 34, that is plus 6, right? So 792 into plus 6. So one can say, if you are taking 2 decimals here, 7.92 into 10 to the power 8 joules. Right now? Okay, that is the energy of the 1 mole of photons released when these X-rays are released, right, from the copper anode. Okay. Hariya my calculation again. Right. Okay. So we have done some questions as well, some calculations as well regarding the hydrogen spectrum and stuff, right? So from this question, we have to stop from this one, right? So complete this question here. So I'll leave the board, right? So we'll meet with the next lesson, right? Goodbye then.